Hi and welcome to this video on complex numbers. Essentially, complex numbers are binomials, and they're written in the form a plus b I. A and b are real numbers and I is the imaginary unit. So let's have a look at some properties of I. So I squared equals minus 1. So essentially I equals the square root of minus 1, or I squared equals the square root of minus 1 squared, which equals minus 1. Now in this complex number a plus bi, let's just put that in a little red square. A is the real part of the complex number, and b is the imaginary part. So a real number can be expressed as a plus 0I. So let's have a little practice with that. So 3 plus 2I is a complex number, and the real part is 3 and the imaginary part is 2. Now if we let z equal a plus ib, then the real part is a and that's sometimes called RE, the real part, and the imaginary part is B, which is sometimes called the imaginary part. It's sometimes, like in electrical engineering, I they call J, and therefore Z equals A plus JB. I allows us to take square roots of negative numbers. Okay, so if we have an example, the square root of negative 9, that equals the square root of 9 multiplied by square root of, multiplied by negative 1. So that would equal the square root of 9 multiplied by the square root of -1. And as we said, the square root of -1 is I. So if we bring that into play, so that would be square root of 9 multiplied by I, which equals square root of 9 is 3, and then I remains the same. We have to do a special note that the square root of -1 equals I, not not that. Square root of -1 is not the same as the square root of I. Okay, if we have the square root of -25, this equals the square root of 25 multiplied by -1. This equals, when we use the properties of square roots, 25 multiplied by square root of -1, and -1 is nothing but I, so that becomes 5I. Square root of 18, or -18 rather, equals the square root of 9 and then multiplied by square root of, multiplied by 2, sorry, multiplied by -1. So this can be then thought of as the square root of 9 multiplied by the square root of 2 multiplied by the square root of -1. Now the square root of 9 is 3, then we have the square root of 2, and the square root of -1 is I. Okay, so we have to remember, note that I squared is -1. So 3I multiplied by 4I is 12I squared, which equals 12 times -1, which equals -12. Similarly, if we have I multiplied by 2I multiplied by -3I, we have -6, -3 times 2 is -6. We have an I squared, and then a separate I. So the I squared is -1, -1 times 6 is 6, and then we have an I left over. Some properties of I. So I to the power 1 is I. Anything to the power 1 is I. Is what is itself rather. So I squared, as we said, was -1. I to the power 3, as we said here, was -1, minus I. So I to the power 4 would be 1. Now let's put a little there, and we're going to have I to the power 5. That would be I. And I to the power 6 is -1. So these powers of I go in cycles of 4. So to calculate higher powers of I, what we do is we take the lowest multiple of 4, and subtract from the exponent. So what do we mean by that? So if we had I to the 99, this equals I to the 96 plus 3. So this would equal I to the 4 times 24 plus 3. So we're left with this, which is the multiples of 4, which we can ignore, and then just use the 3 to get minus I. So we're left with I to the 3 equals minus I. Okay, let's have a look at the addition and subtraction of complex numbers. Now we have to remember that for a complex number, for example 3 minus 4i, we can do x plus yi only if x equals 3 and y equals minus 4. So basically we can add and subtract the real numbers, and we can add and subtract the imaginary numbers together. For example, if we had 2 plus 3i plus 2 minus 6i. So this then would become the real numbers added together, 2 plus 2, and then plus the imaginary numbers added together, which is 3i minus 6i. So this then becomes 4 plus minus 3i, which is 4 minus 3i, and that's the answer. Now let's have a look at subtraction. If we had 6 minus 2i minus 4 minus I. So first of all we have to distribute the minus. And we get 6 minus 2i minus 1 minus 4 minus 1i. So that's 6 minus 2i. When we minus the minus we get plus 4, and then we get plus I. Then when we add the 6 and the 4 we get 10, and minus 2i plus I is minus I, and that's the answer. It's 10 minus I. If we do something a little bit more complex, we could have, let's have a look at our final one. 5 minus 9 minus 2 minus I6 plus 3 minus I4. So again we need to distribute the minus sign. So this will then be 5 minus I9 minus 2 plus I6 plus the 3 minus the I4. Okay, so we distributed the minus sign to give us the plus here. Now all we need to do is get the real numbers together, so that's 5 minus 2 plus 3, and then the imaginary numbers, so that's plus I 6 minus 9 minus 4, and that equals 6 minus I7. When multiplying complex numbers, we FOIL the brackets and then we add or subtract as we did previously. So if we have 2 minus I multiplied by 3 plus 4I. So when we FOIL this out using our FOIL method, 2 times 3, 2 times 4I, so we get 2 multiplied by 3 plus 2 multiplied by 4I plus minus I multiplied by 3 plus minus I multiplied by 4I. This then gives us 6 plus 8I, then minus I times 3 is minus 3I, and then plus minus I times 4I is minus 4I squared. Now we have to remember that this I squared is minus 1, so this becomes minus 4 times minus 1, which is plus 4. So this then becomes 6 plus 8I minus 3I is 5I, and then we have the minus 4 times minus 1, which is a plus 4, and that is our answer. And when we tidy that up, we get 10 plus 5I. Okay, so let's have a look at slightly more complex one. So that was number 1. And number 2, if we had 6 minus I3 multiplied by 2 plus I5 and multiplied by 6 minus I2. Okay, so let's FOIL out the first 2 brackets, and we get 12 minus I6 plus I30 minus I squared 15, and that's multiplied by the second bracket, which is 6 minus I2. Okay, so when we tidy this up, we get 27 plus I 24, and then we've got our second bracket there, which is 6 minus I 2. And when we FOIL this out, we get 162 plus I 144 minus I 54 plus 48. And when we tidy that up, that's 210 plus I 90. And that is our answer. Look at multiplication. Now let's have a look at division. So if we have a complex number divided by a real number, that's quite easy. So if we have 5 minus 4i divided by 3, we can split that into 5 divided by 3 minus I 4 divided by 3, which is 1.67 minus 1.33i. What about dividing a real number by a complex number? So if we had 3 divided by 2i, we do 3 divided by 2i, and then we multiply by I over I, which is essentially multiplying by 1. This equals 3i over 2i squared, and we said I squared was minus 1, so this is then 3i over minus 2, and that equals minus 3 over 2i. Now things get slightly more complicated when we have a real number and a imaginary number as the denominator. For example, if we had 3 over 2 plus I, we get 3 plus over 3 over 2 plus I multiplied by I over I. This equals 3i over 2i plus I squared, and we said I squared was minus 1, so this is 3i over minus 1 plus 2i. Now this answer, although it is an answer, we cannot have I in the denominator, similar to having a square root in the denominator. So we need a method of doing this sum where we're not left with an I in the denominator. So this is not acceptable. So how do we do that? Well, we do that by using something called the complex conjugate. So the complex conjugate, if we have 3 over 2 plus I, this equals 3 over 2 plus I multiplied by the complex conjugate, which is 2 minus I. So 2 minus I is the complex conjugate of 2 plus I. We just reverse the sign binomial under the denominator. So we have to do the same to the top, 2 minus I. So essentially that's 1, so we're multiplying 3 over 2 plus I by 1. This then equals 3, 2 minus I multiplied, and the denominator becomes 2 plus I, 2 minus I. This then is 6 minus 3I all over. When we FOIL this out, we get 4 minus I2 plus I2, which cancel each other out, minus I squared. So that essentially becomes 4 minus, and then I squared we said was minus 1, so it's 4 minus minus 1. So 4 minus minus 1 is 5, so the answer is 6 minus 3I over 5, which we can write as our A plus BI form, and which is 6 over 5 minus 3 over 5I. And that is our answer. Let's have a look at a slightly more complicated division of complex numbers. So if we had 7 minus I4 divided by 4 plus I3. So the complex conjugate we need to use to get rid of the imaginary number on the bottom. So this then we can do as 7 minus I4 divided by 4 plus I3, and we multiply that by the complex conjugate, which is 4 minus I3. So we just reverse that sign in the denominator and then the same on the top, 4 minus I3. When we work that out, the bottom multiplied to the denominators multiplied together is 16 minus 12I plus 12I minus 9I squared. I squared we said was minus 1, so this is 16 plus 9. So the top multiplied together is 7 times 4 is 28 minus I 37 minus 12, and the bottom, the denominator we said was 16 plus 9. When we tidy that up, that's 16, 28 minus 12, 16 minus I 37, and 16 plus 9 is 25. So this is 16 over 25 when we put it in the form of A plus IB minus I 37 over 25. And if we work that out, that's 0.64 minus I 1.48. And that is our answer. Let's have a look at complex numbers and their applications. So in this one we're going to have a look at electrical circuits. And here J equals I. So the impedance in one part of a circuit is 2 plus J 7 ohms, and in another part 4 plus J 6 ohms. What's the total impedance? So we just add these two complex numbers together. So the real part's 4 plus 2 is 6, and then we have the imaginary parts. J7 minus J6 is J1. And this one, the voltage in a circuit is 45 plus J10 ohms. The impedance is 3 plus J4 ohms. What's the current? So here we have to use the formula E equals I multiplied by Z. So here E is the voltage in the circuit, the impedance is Z, and we want to find the current I. So we get 45 plus J10 equals I, 3 plus J4. So to get I we divide, so we get 45 plus J10 divided by 3 plus J4 equals I. Now, as we did before with the division of complex numbers, 45 plus J10 divided by 3 plus J4. We multiply this by the complex conjugate, which is we reverse the sign on the denominator, so we get 3 minus J4, 3 minus J4, and that equals I. So when we multiply that out, we get 135 plus J180 plus J130 minus J squared 40, and all that is over 9 minus J squared 16. And as we said before, J squared equals minus 1. So this equals 175 minus J150 divided by 25, which equals, if we want this in the form of A plus JB, so this would be 175 over 2 minus J150 over 25. Sorry, this should be 25 as well. And that becomes, when we divide by the 25, our answer is 7 minus J6 amps. And that is our answer. Complex numbers are used in solving cubic equations. Cubic equations where the method involves using the quadratic formula and the square root, b squared minus 4ac. So if the square root is of a negative number, we need to use complex numbers. So let's have a look at where we don't use complex numbers. Just a quick revision. So we have x cubed minus 3x plus 2 equal 0. Now we look at where we have this 2, which is usually the c in the equation. which is we look at the factors of 2, which are 1, minus 1, 2 and minus 2, and we see when we put these into the equation which one gives us 0, and when we do that with 1 we get 1 is a solution. So therefore x minus 1 is a factor. So now to get the quadratic equation we do some algebraic division. So to do that we put the equation underneath. So we have x cubed. Remember there's no x squared, so we have to put 0x squared minus 3x plus 2, and all that's divided by x minus 1. Right, so how many times does x go into x cubed? So that's x squared. So we bring the x cubed at the bottom. X squared times minus 1 is minus x squared. Then we subtract. Here we get 0. X squared minus x squared is plus x squared. We bring down the 3x. How many times does x go into x squared? That's 1, so that's plus x. So we have x squared on the bottom. And then x times minus 1 is minus x. And we subtract. So when we do that, we get 0. X squared minus x squared is 0. Minus 3x minus x is 2x. So that's minus 2x. And we bring down the 2, so that's plus 2. And then when we multiply, when we go x into minus 2x, we get minus 2. And then when we multiply them by the minus 2, we get 2x plus 2, and take away, and that ends up as 0. So we have x minus 1 multiplied by the quadratic x squared plus x minus 2. When we factorize this quadratic we get x minus 1 and x plus 2, and our roots are 1 from here, 1 from here, and 2. So here we have 1 twice, so our actual graph, if we do a quick sketch, will look, if we have minus 2, that should be, if we have minus 2 here and then going that way, it'll go up and go through here at 2, so it's going to go up here through the 2 and then just touch here at 1 and then back up. So this is the x-axis, this is the y-axis, 2, 1, 2. Okay, let's look at a cubic equation where we can't find the roots so easily and we have to use the quadratic formula. So find the roots of x cubed minus 4x squared plus x plus 26 equals 0. So first of all, let's try and find some factors of 26, which when we put them into the equation gives us a root. So we let f of x equal x cubed minus 4x squared plus x plus 26, and we find that f of minus 2 equals 0. Therefore x equals minus 2 is a root, and x plus 2 is a factor. Okay, let's do our algebraic division. So if we do that quickly, we have our x plus 2 here, and we've got all our x's as x3 minus 4x squared plus x plus 26. So how many times does x go into x cubed? We get x squared, so that'll be x cubed plus 2x squared. So we subtract, we get 0 minus 6x squared, bring the x down, we get plus x. How many times does x go into 6x squared? We get minus 6x squared, we get minus 6x. So we then put the 6x squared on the bottom. 6x times 2, we get minus 12x. Subtract, we get 0. X minus minus 12x is 13x, and then plus 26 when we bring the 26 down, and then we got the 13x here, and x into 12x, oh sorry, x into 13x goes plus 13, and here we have 26. When we subtract, we have 0. So it can be, this quadratic can be factored as x plus 2 and the quadratic x squared minus 6x plus 13 equals 0. Now we can't factorize this easily, so we have to use the quadratic formula where a equals 1 here, x squared, b equals minus 6, and c equals 13. So here we get x equals minus b, we get 6 plus or minus square root minus 6 squared minus 4 times 1 times 13, and all that is over 2a, which is 2 multiplied by 1, is equals 6 plus or minus the square root of 16, or minus 16 rather, and all that is over 2. This 2 cancels, that's 6, we're left with a 3. The plus or minus square root of minus 16 is plus or minus 4i, and when we divide that by 2, that becomes plus or minus 2i. So x is minus 2 or 3 plus 2i, and minus 2i as a conjugate pair. When we draw this cubic out, we get it going through the minus 2 as shown here, and then going up through 26 on the y-axis, which is shown by this part of the equation. Then it comes down and doesn't have any other real roots, and then goes back up. Although we can't evaluate a complex number as a real number, we can represent it graphically, and we'll have a look at that now. In the usual system of plotting numbers, the 3 could be represented as a line from the origin. So if we have the origin on this line is here, and then we have 1, 2, 3, and then minus 1, minus 2, minus 3. Minus 3 goes to the left, and obviously 3 goes to the right. The line represents the magnitude by its length. So the length of this line is the magnitude plus 3, and on this side minus 3. And the arrow represents the direction. Similarly, if we multiply plus 3 by minus 1, we get minus 3. So this is like rotating this plus 3 through 180 degrees, and we get the minus 3. So multiplying by minus 1 is equivalent to multiplying by j2, so, or i2. So our j squared or I squared equals minus 1. So if we multiply by I, that would be similar to rotating the line plus 3, which is over here, by 90 degrees. So if we did multiplied by I, which is what we're doing there, it's rotating that by 90 degrees, and we get I3. The I factor always turns the vector through 90 degrees. So this is a vector. It always has direction and magnitude. And I is always anti-clockwise. We can denote two reference lines, the x-axis and the y-axis. So the x-axis, when we're dealing with complex numbers, is called the real axis, and the y is called the imaginary axis. And we draw the points for the complex numbers on the complex plane. And this whole diagram that we use with the imaginary axis and the real axis is called the Argand diagram. So let's have a look at plotting 3 plus I2. So for this we go along the real axis by 3, so it would be 3, and we go up the imaginary axis by 2, so this would be 2. So our point would be here. So this point represents, on the complex plane, the complex number 3 plus I2, and if we wanted a single vector to represent 3 plus I2, it would be this from the origin to the point on the complex plane, and that would be 3 plus I2. If we wish to represent 3 plus 2 as the sum of two vectors, we must draw them as a chain. So we'd have the vector representing 3 and then the vector representing 2. So this would be 3 plus 2 equals 5. Similarly, when we're adding complex numbers, we need to draw the vectors where we line up the tail of the vector with the arrow and we form a chain. For example, if we had z1 equals 5 plus I2 and z2 equals 2 plus I3, and we wanted to do the addition graphically using the Argand diagram. So we draw this first vector z1, so that's 5 along the real axis and 2 along the imaginary axis, which is there. So from the origin we draw the vector to that point, so up to there. Then we want z2, which is 2 along the real axis, 3 along the imaginary axis, from the origin up to there. Now what we need to do is we need to move the z2 to line up with the z1. So this arrow, this vector has to be moved across over here. So we can do this in two ways. One way is to use a compass. So we measure this vector, the magnitude, and we draw a semicircle here. Okay, and then we measure z2, we've done that, and we measure z1, and then we measure that from the end of z2, and we get the point here. So this is our z2 after we've moved it across. So that it lines up with the tail to point with z1, and we get a chain. This can be thought of as forming a parallelogram. So if we draw a dotted line to form our parallelogram like this, and the resultant vector is the diagonal of the parallelogram, so that would be from the origin to that point, the diagonal, and that would be z1 plus z2. So if we label these points, so we have A, P, B, and then the origin. AP equals OB, both in magnitude and in direction. OA equals BP, and our sum Z1 plus Z2 equals OP. Okay, we're going to look at graphically subtracting vectors. We do this by using a little trick and then adding the vectors. So if we want to do Z1 plus Z2, we say it's going to be Z1 plus minus Z2. So if we have Z1 as a complex number 5 plus I2 and Z2 as 2 plus I3. So let's draw these on our Argand diagram. So our Z1 would be along the real axis 5 and up 2. So that would be here. And then our Z2 would be along the real axis 2 and up the imaginary axis 3, which would be here. So we're going to draw this as a dotted line, because what we need to do is we need to draw the negative version of this, and the negative version simply goes the other side. It's a reflection along this dotted axis. So that would be where this was 2 across 3 up, it would be 2 across 3 down. So this would be our negative Z2. And we simply add now our Z1 and Z2. So how do we do that? Well, we need to move the minus Z2 over here to the end of our vector Z1. So if we look, we went down 1, 2, 3 and across 2, so we'll go down 1, 2, 3 and across 2. 1, 2, 3 and across 2. So that will take us to here. This would give us our vector. So this is our minus Z2 again. This is our parallelogram. And our resultant vector in red would be from here to there. So if we label this now, this is our origin, A, B, P, Q. So our OA is Z1, our OP is minus Z2, and our resultant vector OQ is Z1 minus Z2. Okay, let's now put what we've learnt into practice by doing a slightly more complicated graphical addition of complex numbers. So we'd have 4 plus I2 plus minus 2 plus I3 minus 1 plus I4. So this is Z1, this is Z2, and this is Z3. So let's first of all draw our Z1, which is 4 along the real axis and 2 along the imaginary axis. So this is our Z1, let's just go to the origin. Okay, Z2 would be minus 2 along the real axis and 3 along the imaginary axis. So this is our Z1, this is our Z2. Now we want to draw our resultant vector, which would be Z3. So let's add our Z1 and Z2 to form the sides of a parallelogram. So this we're going, let's have a look, 2 across and 3 up. So this would be from this point 2 across and 1, 2, 3 up. So it go up there. So this is our Z2 when we brought it over to the end of Z1 to form a chain. Now we draw our parallelogram, which would be here, and our resultant vector in green would be from the origin to that point there. This is now Z1 plus Z2. Now we need our Z3. The Z3 is essentially minus 1, 4, and we want a minus of that because we're subtracting it. So instead of going to minus 1 along the real axis to 4 along the imaginary axis, we're going to go 1 along the real axis, minus 4 along the imaginary axis, and this gives us minus Z3. Now we want the resultant vector, so this would be Z1 plus Z2 plus minus Z3. So we move the minus Z3 from our Z1 plus Z2. I'm at the wrong point here. So for we need to move the minus Z3 to the end of this vector. So this would be 1 across and 4 down, 1, 2, 3, 4 to here, and this would form our side of our this would form the side of our parallelogram. So that's at the other side of the parallelogram, and our resultant vector Z1 plus Z2 plus Z3 is shown in red. So this would equal, the resultant vector equals 3 plus I, which is Z1 plus Z2 minus Z3. It's often convenient sometimes to express a complex number, a plus ib, in a different form. So if on our Argand diagram we have a vector OP, so let's draw that vector in here. So this is the origin, this is P, so that's our vector OP, and R is the length of the vector, and the angle it makes with X is called theta. So this is the imaginary axis and this is the real axis. So using Pythagoras, if we have a line down to the x-axis, we can call this B and this is A. So the complex number is A plus IB. So using Pythagoras we get R squared equals a squared plus b squared. So r equals the square root of a squared plus b squared. And also tan theta equals b divided by a. So theta equals inverse tan, which is tan to the minus 1 b over a. Now also we have a equals r cos theta and b equals r sine theta. So since z equals a plus ib, we can write z as r cos theta plus I r sine theta, and then this becomes, when we take the r outside, factor it out, r cos theta plus I sine theta. This is called the polar form. This is called the polar form of the complex number. When we are graphically representing a complex number on an Argand diagram, say it was, for this one, z1 equals 3 plus I4. So we go 3 along the real axis and 4 along the imaginary axis, and we draw a line from the origin to that point. This distance of the vector is called r. R is the magnitude of the vector, or the length, and that has a special name. So r is called the modulus. It's also named z, and mod z, or short z with a modulus sign around it. So let's have a little practice drawing different complex numbers. So if we had this on a quadrant diagram, it would be minus 3 and then going up 4, minus 3, 4. So z2 would be minus 3 would be the real, and plus I4 would be the imaginary part. On this one, z3, we'd have again 3 or minus 3 along the real axis and minus 4 along the imaginary axis. So this would be z3 equals minus 3 minus I4. Here we have z4, so the vector is in this fourth quadrant. So here we have again 3 along the real axis and minus 4 along the imaginary axis. So Z4 equals 3 as the real, and then minus I4. Now, from Pythagoras we know that R squared equals A squared plus B squared. So R in each of these cases is the square root of A squared plus B squared. When we look at the argument, or also known as arg Z, this is the angle theta, and it's the angle between the positive real x-axis and the complex number. In actual fact, theta has two values, more values, which differ from each other by 2 pi. So if we have 2 pi k, and k is 1, 2, 3, or minus 1, 2, 3, then when we multiply those by 2 pi, those can be all values of theta. Now tan theta equals, if we draw a line down and across, so in the first case for Z1, tan theta would be the opposite, which is 4 over the adjacent, which is 3. Now what we've got to bear in mind in these different quadrants, theta goes from the positive axis, as we said, to the complex number. So in this case, this is theta. In this case, this is theta, and this would be, say, alpha. In this third case, this would be minus theta, and this would be the alpha, and in this case, this would be minus theta. So the two cases we've got to be careful with are here, when the complex number is in the second quadrant. Here, actually, theta, let's do this in red, theta would be pi minus alpha. Right, we're going to work in radians. Let's just do another note there. Theta is in radians usually, and within the range minus pi to pi. So in this case, theta would be pi minus alpha, and then the other case is, this one was Z3 when it's in the third quadrant, so theta would be minus pi minus alpha. So those are the two cases we've got to bear in mind, as well as this fourth case where we're going anti-clockwise, and that would be minus theta. So let's have a look in these complex numbers. Let's find out arg z. So first of all, here tan theta be 4 over 3. Theta is tan minus 1, the inverse tan of 4 over 3, and when we switch our calculator to radians, which is 0.9 radians to one significant figure. So arg of z, of z1 in this case, is 0.9 radians. In this case, first of all we need tan alpha, that's 4 over 3. So tan minus 1 alpha is 0.9 radians, and our arg z2 is pi minus 0.9 radians. Okay, let's have a look at this number 3. So our tan alpha would be 4 over 3. Tan minus the inverse tan, 4 over 3, 0.9 radians. And then our arg z3 would equal minus pi minus 0.9 radians. In this z4, tan theta equals 4 over 3, so tan minus 1 equals 0.9 radians. So z4 equals minus 0.9 radians. So in this case we have to remember that this is minus theta. Okay, so let's have a quick look. Let's have a quick look at writing in polar form. If we had z equals 1 plus I, and we were asked to write that in polar form. First of all, let's draw our Argand diagram. So just do a quick sketch. So this is 1 along the real axis and I, which is 1 along the imaginary axis. So draw in our vector, which will be there. So this would be I, this would be 1. So our R, or our mod Z, would equal square root of 1 squared plus I squared, which is the square root of 2. Tan theta equals 1 over 1, which is 1. So theta is pi over 4. So our polar form then for Z equals square root of 2 cos pi over 4 plus I sine pi over 4. Okay, let's quickly do another one. So if they gave us W equals square root of 3 minus I. So quickly draw our Argand diagram, and it goes somewhere like this in the fourth quadrant. This would be the real square root of 3, and this would be negative I. Okay, so R modulus of W, or mod W, equals square root of square root of 3 squared plus minus I squared. So this becomes 3 minus 1, which is 2. So tan theta is minus 1 over square root of 3, which makes theta minus pi over 6. So our polar form of this original complex number then becomes w equals 2 cos minus pi over 6 plus I sine minus pi over 6. I'm going to have a look at de Moivre's theorem now. And what this says is that if z equals r cos theta plus I sine theta, and if n is a positive integer, so if n is a positive integer, then z to the power n, or our complex to the power n, equals r cos theta plus I sine theta all to the power n, which equals Rn cos theta, cos n theta plus sine n theta. So what does that mean? So to take the nth power of a complex number, what we do is we take the nth power of the modulus, and then we multiply the argument by n. So let's have a look at this. So if we have a half plus a half I to the power 10. So drawing this on an Argand diagram, we'd have a half, and then this would stop here at a half on the imaginary axis. This would be the real axis. So our r, let's just do this here, would be square root of a half squared plus a half squared, which will give us r equals square root of 2 over 2, and our tan theta, which is here, equals 1, which is theta equals pi over 4. So now let's put that in our equation. So we'd have a half plus a half I equals square root of 2 over 2, and then we'd have cos is pi over 4 plus I sine pi over 4. And by De Moivre's theorem, we have a half plus a half I to the power 10. This would equal square root of 2 over 2 to the power 10, and then we have cos pi over 4 times 10, which would be 10 pi over 4, and plus I sine 10 pi over 4. This equals 25 over 2 to the power 10 cos 5 pi over 2 plus I sine 5 pi over 2, which equals 1 over 32I. Going to have a look at when we multiply complex numbers together, what happens. So if we have, let z1 equal r1 cos theta 1 plus I sine theta 1, and then if we have z2 equals r2 cos theta 2 plus I sine theta 2. We'll multiply these two together, z1 and z2. This would equal r1 r2 cos theta 1 plus I sine theta 1, and then we multiply that by cos theta 2 plus I sine theta 2. When we work that out, that's r1 r2 cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, and plus I sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. Now let's have a look at a addition. If we have a look at this, this is nothing but this is nothing but the addition formula for sine and cosine. So addition formulas. Sine and cosine. Let's just have a review of that, which says that cos A plus B equals cos A cos B minus sine A sine B. So here we have cos A cos B minus sine A sine B, and then also sine A plus B equals sine A cos B plus cos A sine B. And here we have sine A cos B plus cos A sine B. So we can write this now as R1, R2 cos theta 1 plus theta 2, and then plus I sine theta 1 plus theta 2. So this says to multiply complex numbers we multiply the moduli, which is R, and add the arguments, which we're doing here. So let's have a quick look. So this is our rule: multiply the moduli and add arguments. So if we have a quick look at the product, 1 plus I and square root of 3 minus I. So those two complex numbers. So I, or 1 plus I, in polar form is square root of 2 cos pi over 4 plus I sine pi over 4, and square root of 3 minus I is 2 cos minus pi over 6 plus I sine minus pi over 6. So when we multiply them together, so it's 1 plus I multiplied by square root of 3 minus I. This is 2 and square root of 2 multiplied together, 2 square root of 2, and then we add the arguments, so this would be cos pi over 4 minus pi over 6 plus I sine pi over 4 minus pi over 6. And this equals 2 square root of 2 cos pi over 12 plus I sine, and this would become pi over 12. So we're multiplying the moduli and we're adding the arguments. Okay, let's have a look at using De Moivre's theorem. So it says that if we have a complex number to the power n, this is r cos theta plus I sine theta all to the power n, and this equals r n cos n theta plus I sine n theta. So if we were asked to express cos 3 theta in terms of cos theta. This means that cos 3 theta plus I sine 3 theta equals cos theta plus I sine theta all to the power 3. So let's take this side and then let's do an expansion. So this would be nothing but cos theta plus I sine theta multiplied by cos theta plus I sine theta multiplied by cos theta plus I sine theta. Okay? When we FOIL that out, we get cos cubed theta minus 3 sine squared theta cos theta plus 3 I sine theta cos squared theta, and then finally minus I sine squared, no, minus I sine cubed theta. So then we evaluate the real parts. So our cos 3 theta, so we ignore the imaginary parts with the I. Our cos 3 theta is equal to cos cube theta minus 3 sine squared theta cos theta. So this equals cos cube theta minus, now we can use trig identities, so this becomes 3, 1 minus cos squared theta, and then our cos theta on the outside. When we multiply that out and add the like terms, we get 4 cos cubed theta minus 3 cos theta. And that is our answer. So we used De Moivre's theorem there. If we wanted to confirm that, we could use some trig. So let's do an OR. So we say our cos 3 theta equals cos 2 theta plus theta. Now from our cos A plus B, this is cos A cos B minus sine A sine B, so that equals cos 2 theta cos theta minus sine 2 theta sine theta. Okay, so we're applying our cos A plus B. Now we want to see what we can do with these parts here. So we can use our trig identity. So we have 2 cos squared theta minus 1, and then our cos theta on the outside, minus sine 2 theta is sine theta cos theta, so this becomes 2 sine theta cos theta, and then our sine theta. So this is now, when we multiply it out, 2 cos cube theta minus cos theta minus multiplying this out, we get 2 sine squared theta cos theta. So using our trig identity on here, we get 2 cos cube theta minus cos theta. So applying our trig identity, we get 2 1 minus cos squared theta, and that's multiplied by cos theta. So this then finally we get 2 cos cube theta minus cos theta minus 2 cos theta minus 2 cos cubed theta. And then when we add the like terms, this equals, just move that up a little bit, 4 cos cube theta minus 3 cos theta. So using De Moivre's theorem, we've just proved gives you the same results. If we have a look at the points which satisfy mod z equals r, this forms a circle at the center of the this makes a circle with the origin as the center and the radius is r. So if we plot this on our Argand diagram, so if we have this as our r, and then we plot the radius, or we plot the locus or the points this makes around the quadrants, it goes like that. So all the points on the circle have the same modulus. Or the same size. Now if we take z equals x plus iy, the modulus or mod z is the square root of x squared plus y squared, and this equals r. And if we look, x squared plus y squared equals r, and this is the Cartesian equation for a circle. With the origin at its center, so O being there, and radius r. Sometimes you can be asked to find the locus of a point and give its Cartesian equation. So if we're asked to find locus z1 minus z2, or z1 minus z2 equals r, so z1 equals x plus iy, and z2 equals u plus iv. v. Then from above we had x plus iy and we're doing minus u minus iv. This is equal to r. Therefore x minus u, when we get the real parts together, minus I y minus v equals r. When we take the square roots, this would be x minus u squared plus y minus v squared equals r. So x minus u squared plus y minus v squared equals r squared, and this is the equation, as we said, for the circle. So this would be a circle, center uv and the radius r. Here we're going to have a look at equating two complex numbers, and then by looking at that technique for finding the square root of a complex number. So if we have complex number 3x plus 5i equals 6 minus 10y I. So what we do first is we equate the real numbers. So we have the 3x as the real number is equal to 6, so 3x equals 6, so x equals 2, and then the imaginary numbers, we have 5, so the 5 will equal to minus 10y. So the y is equal to minus 5. Okay, so let's have a look at that in finding the square root of a complex number. So we're going to find the square root of minus 21 minus 20i. So we have z squared equals minus 21 minus 20i, and our goal is to find z. So how do we do this? First of all, we have to know that our z squared is our complex number a plus bi. So if we have our z, which we want to find, would be a plus bi squared. So a plus bi squared, that is the first squared, a squared, plus 2abi, and then plus the imaginary number squared, but I squared is minus, so this becomes a minus b squared. Now we equate the real parts, so the real is a squared minus b squared, and that is equal to our real part in this equation, which is minus 21, and our imaginary parts, which is 2ab, and that is equal to our imaginary part of the complex number, which is minus 20. Now the other thing is, because the modulus, as we discussed previously, is the same for the root, a squared plus b squared, so also this is quite important, because the modulus is the same, our a squared plus b squared is equal to the square root of a squared plus b squared, or minus 21 squared plus minus 20 squared. So if we call this 1, call this 2, and call this equation 3, when we add equation 1 and 3, we get 2a squared equals, this is 29, so 2a squared would equal 29 minus 21, so a is minus 2, or 2. When we plug this into our equation, our a, so now we plug a into equation 2, we get b equals 5 and b equals minus 5. So therefore our roots in complex form is minus 2 plus 5i and 2 minus 5i. Cut a slightly more difficult square root of a complex number. So if we have z equals 9 plus 4i, so our z squared would equal 9 plus 4i, and our z, because it's z we want to find, is 9 plus 4i all squared, because we want to find z. So we identify our real parts. So again, a squared plus bi squared equals a squared plus 2abi minus b squared. Okay, so we identify our real parts, and our real parts are a squared minus b squared equals 9. Have that equation 1, so that's real. Our imaginary, equating those, we get 2ab equals 4. That's our equation 2. Now because the modulus is the same, we have a squared plus b squared equals the square root of a squared b squared, which is 9 squared plus 4 squared, and we'll have a equals square root of 97. Okay, so we don't get a, so we're left with a square root. So now when we add 1 and 3, So this is our 3. So a squared, or 2a squared actually, 2a squared becomes 9 plus our square root of 97. And then using equation 2, we get a equals square root of half 9 plus square root of 97. So we can either have that, or because we've got the square root, we can have a equals minus square root of half 9 plus square root of 97. Now using equation 2, b equals square root 2 over 9 plus square root of 97, or b equals minus 2 square root of 2 over 9 plus square root of 97. So our square roots, we have 2, z equals, and z equals a half 9 plus square root of 97 minus a half 9 plus square root of 97. This would be plus 2i, and then our 2 over 9 plus square root of 97, and this would be minus 2i, 2 over 9 plus square root of 97. Okay, we're going to have a look at the exponential form of complex numbers, and for this we have to look at the series. So if we look at the series for the exponential e to the x, we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial, and so on. If we have a look at the series for sine of x, we have x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial, and so on. For the series for cos x, we have 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial, and so on. And the series continues. Now if we take the series for e to the x, if we replace x with I theta, for e to the x now then becomes 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the power 4 over 4 factorial, and so on. This is 1 plus I theta plus I squared theta squared over 2 factorial plus, this should be cubed, I cubed theta cubed over 3 factorial plus I to the power 4 theta to the power 4 over 4 factorial, and so on. So this we can then write as 1 plus I theta minus theta squared over 2 factorial, bearing in mind our powers of I, and then this then becomes minus I theta to the power 3 over 3 factorial plus theta to the power 4 over 4 factorial, so on. Now the final step, we can write this as 1 minus theta squared over 2 factorial plus theta to the power 4 over 4 factorial, and so on, and we add I theta minus theta cubed over 3 factorial plus theta to the power 5 over 5 factorial, and so on. So therefore r cos theta plus I sine theta, this is cos theta and this is sine theta, we can rewrite as RE, because we're discussing the powers of V. So it can be written as RE to the I theta. And this is the exponential form of the complex number. And theta must be in radians. Okay, we want to change 5 cos 60 degrees plus I sine 60 degrees into exponential form. So we have r equals 5 and our theta equals 60. In radians, that's pi over 3. So this now becomes, in exponential form, r, which is 5, e, and then I to the power I, pi over 3. Let's have a note here. So if we had 5 e to the minus I pi over 3, that would simply be, in polar form, 5 cos 60 or cos pi over 3 minus I sine pi over 3 or 60 degrees. It's better to stick to pi over 3 because we want to work in radians. Finally, we're going to have a look at the logarithm of a complex number. So if we had z equals r e to I theta, then we can rewrite this as natural log of z equals the natural log of r plus I theta. So if z equals natural log of r plus I theta, we have z equals 6.42 e to the I 1.57. So this would mean that natural log of z equals the natural log of 6.42 plus I 1.57, and this is in complex form. One point 8594 plus I 1.57. So if we were given, for an example, let's make this our final example in this, e to the 1 minus I pi over 4. And we wanted to write this in polar form. Which is a plus ib. So this is nothing but e to the power 1, e to the minus I pi over 4. This equals e cos pi over 4, because we're working in radians, and the minus goes here, minus I sine pi over 4. This equals e 1 over square root of 2 minus I 1 over square root of 2. And finally the answer is e over square root of 2 1 minus I.